Consider a Solow growth model where the production function is y equals k to the power of 0.5, L to the power of 0.5. The saving rate is equal 0.3, the depreciation rate is delta equals 0.05, and the population growth rate is n equals 0.02. Assume there is no technological progress, g equals 0. Write the per capita production function y equals f of k, where y equals y by L and k equals kl. Explanation: the Solow model often analyzes variables in per capita or per effective worker terms to focus on the determinants of the average standard of living. To convert the aggregate production function y equals k to the power of 0.5 L to the power of 0.5 into per capita terms, we divide both sides by L. Solution: given production function y equals k to the power of 0.5, L to the power of 0.5, divide both sides by L is to frac y L equals frac k to the power of 0.5 L to the power of 0.5 L. Recall that L equals L to the power of 1.0, so L to the power of 0.5. L to the power of 1.0 equals L to the power of 0.5 minus 1.0 equals L to the power of minus 0.5. Frac y L equals k to the power of 0.5, L to the power of minus 0.5. Frac y L equals frac k to the power of 0.5, L to the power of 0.5. Frac y L equals left, frac kl right, to the power of 0.5. Now substitute y equals y by L and k equals k by L is to y equals k to the power of 0.5. Per capita production function y equals k to the power of 0.5. B. Derive the fundamental equation of capital accumulation in per capita terms. Explanation: this equation describes how the capital stock per capita, K, changes over time. It's the core of the Solow model. The change in capital per capita, K, is determined by two forces. 1. Investment per capita. This adds to the capital stock. It's the saving rate, S, multiplied by output per capita, Y, since saving equals investment in this model, SY. 2. Break-even investment. This is the amount of investment needed just to keep the capital per capita, K, constant. It accounts for capital that depreciates, delta K, and new capital needed for the growing population, NK. The fundamental equation is K equals SF of K minus valley delta plus NK. Solution: the aggregate capital accumulation equation is K equals SY minus delta K. To convert this to per capita terms, K, we use the rule for the derivative of a ratio. K equals frac, KL.K equals frac, d of KL dt equals frac.KL GL dt equals frac.KL K.L squared. We know that L by L equals N, population growth rate, so L equals NL. Substitute K equals SY minus delta K and L equals NL. K equals frac, SY minus delta KL, K of NL, L squared. K equals frac, SYL minus delta KL, NKLL squared. K equals S frac Y, LL squared minus delta frac K, LL squared minus N frac K, LL squared. K equals S frac YL minus delta frac K, L minus N frac KL. Substitute Y equals Y by L and K equals K by L is to K equals SY minus delta K. NK. K equals SY minus delta plus NK. Now substitute y equals k to the power of 0.5 from part A is to K equals sk to the power of 0.5 minus delta plus NK. Given S equals 0.3, delta equals 0.05, N equals 0.02. K equals 0.3 k to the power of 0.5 minus 0.05 plus 0.02 k. K equals 0.3 k to the power of 0.5 minus 0.07 k. Fundamental equation of capital accumulation. Dot K equals 0.3 K2, the power of 0.5 minus 0.07 K. C. Find the steady state level of capital per effective worker, K to the power of. Explanation. The steady state is a long-run equilibrium where the capital stock per capita, K, no longer changes, that is, dot K equals 0. At this point, the amount of investment per capita is just enough to cover depreciation and the needs of new population members. Solution. Set dot K equals 0, 0 equals 0.3 K2, the power of 0.5 minus 0.07 K. Move the negative term to the other side. 0.07 K equals 0.3 K2, the power of 0.5. Divide both sides by K to the power of 0.5, assuming K greater than 0, 0.07 K to the power of 1 minus 0.5 equals 0.3. 0.07 K to the power of 0.5 equals 0.3. Solve for K to the power of 0.5. K to the power of 0.5 equals frac 0. 0.07. K to the power of 0.5 equals frac 37. Square both sides to find K to the power of. Mind sahi is to nechishil nechiquare equals left. Frac 37 right. Squared K to nechiquare equals frac 949 K to nechiquare of asterisk approx 18.37. Steady state level of capital per capita, who lived in the power of, equals frac 949 or approximately 18.37 units. D. Calculate the steady state level of output per effective worker, y to the power of. Explanation. Once we have the steady state level of capital per capita, k to the power of kado, we can find the steady state level of output per capita, y to the power of kado, by plugging k to the power of into the per capita production function derived in part A. Solution. Per capita production function, y equals k to the power of 0.5. Substitute k to the power of equals frac 949. Y to the power of equals left frac 949 right. To the power of 0.5. Y to the power of equals frac square root of 900 square root of 49. Y to the power of equals frac 37, y to the power of asterisk approx 4.29. Steady state level of output per capita, y to the power of equals frac 37 or approximately 4.29 units. E. What is the golden rule level of capital per effective worker, K_GR? Explanation. The golden rule level of capital is the steady state level of capital per capita that maximizes consumption per capita. In the Solow model, consumption per capita is output per capita minus investment per capita is to C equals YSY. Since at steady states Y equals delta plus NK, we can write K equals Y minus delta plus NK. To find the golden rule, we maximize consumption per capita with respect to K. This requires the marginal product of capital, MPK, to be equal to the sum of the depreciation rate and the population growth rate, i.e., the effective depreciation rate. MPK equals delta plus N. Solution. First, find the marginal product of capital, MPK, from the per capita production function, y equals k to the power of 0.5. MPK equals frac dy dk equals frac d of k to the power of 0.5 dk. MPK equals 0.5 k to the power of 0.5 minus 1. MPK equals 0.5 k to the power of minus 0.5. MPK equals frac 0.5 k to the power of 0.5. Now set MPK equal to delta plus N. A very tall man Jashil is to frac 0.5 k_gr to the power of 0.5 equals delta plus N. Substitute the given values for delta and N. Frac 0.5 k_gr to the power of 0.5 equals 0.05 plus 0.02. Frac 0.5 k underscore gr to the power of 0.5 equals 0.07. Solve for k underscore gr to the power of 0.5 is to k underscore gr to the power of 0.5 equals frac 0.5 0.07. K underscore gr to the power of 0.5 equals frac 57. Square both sides to find k underscore gr is to k underscore gr equals left frac 57 right squared. K underscore gr equals frac 2549. K underscore gr approx 51.02. Golden rule level of capital per capita k underscore gr equals frac 2549 or approximately 51.02 units. Interpretation: this value of k underscore gr would lead to the highest possible sustainable level of consumption per person in the long run. Since our calculated steady-state capita go through the power of asterisk approx 18.37 is less than the golden rule capital K underscore gr approx 51.02, it implies that the economy is currently undercapitalized from a consumption maximization perspective. To reach the golden rule, the economy would need to save, and thus invest, a higher proportion of its output, which would lead to a temporary decrease in consumption, but a permanently higher level of consumption in the new higher steady state.